Now let's apply Noether's theorem in a real-life example. Consider this situation: a ball falling from a given height. Now, what's the quantity that's conserved here? It's energy. It's also important to note that the ball naturally falls in such a way that the Lagrangian is minimized. Now, according to Noether's theorem, in this example, the system is symmetrical in time. What this means is that the ball can fall at any given time and the energy would still be conserved. Mathematically, this is seen as this equation. What this equation tells us is that the derivative of the Lagrangian does not change over time. Physically, this means that the energy of the whole system will be conserved. Now that we've successfully applied the theorem, it's important to understand why this theorem is so useful. You see, without this theorem, understanding the fact of time symmetry without knowing that the energy is conserved would be near impossible. In fact, the calculations that took 2 lines would take pages.
Let's now consider some further applications of Noether's theorem. In general relativity, it was found that the theory implied that energy is not conserved in some situations. However, Noether helped prove that this wasn't in fact an issue, as in those scenarios, the time symmetry required for energy conservation was not present. One such example is cosmological redshift, the process in which photons from distant galaxies have their wavelengths stretched due to the expansion of space. These photons will lose energy as they are redshifted, but where does this energy go? Thus, the conservation problem. But using Noether's theorem, since space is expanding on cosmological scales, the processes that are affected by that expansion will have their governing equations change with the expansion of space. So by definition, energy is not an inherent conserved quantity. This is due to the space-time fabric not being symmetrical in time. Let's consider a car driving at constant velocity on a flat plane. I think you'll agree that it will have the same total energy and the same equations of motion regardless of which direction it's driving. So we can say that the system is symmetric to translation in that 2D plane. And it turns out that any system with a symmetry in space will have conservation of momentum. But if we consider throwing the car into the air by translating it in the vertical direction, conservation of momentum is not obeyed in this 3D system since the potential energy of the car changes depending on its height.